Okay, hi guys. I'm Mr. Larson. Now you get a face and a voice to go with the typing. Sometime it'd be fun to be able to do a fuse meeting, maybe so that we could all see each other. It's kind of weird just doing the typing back and forth. But anyway, as I promised you, I thought I'd try a video presentation this week. I've gotten a lot of questions about these limits that go to infinity and what all that means as far as does the limit exist or doesn't the limit exist, and increasing without bound. So I just wanted to take a few minutes and talk about that before we move on with this week. Now, I used to get teased when my youngest son was in my calculus class. It seemed like a lot of his classmates would tease him about, oh, your dad must have a whiteboard in your basement and you guys after school, all you do is go home and solve problems on the whiteboard. And that was far from the truth. We never had one. However, I am standing in my basement right now and I do have a whiteboard behind me. But this is a new addition to the basement. What I've got drawn up here is the function absolute value of 1 over x, and you've seen that a number of times through this first unit. And I just wanted to talk about where the limit doesn't exist in discontinuities. This is the classic shape of a function who's got a limit that goes to infinity. The reason that we say it still exists, the limit exists even though there's this discontinuity here, is if we were able to zoom in, and you can do this on your graphing calculators, but if we were able to zoom in and look at what's up above the whiteboard really high, what we'd find is as you get closer and closer to the y-axis, to the point where x is equal to 0, no matter how close you get to the 0 mark, you can still find, if you go put an x value in and you go up there, you will find a y value. There is a y value that does exist. The only place that it doesn't exist is right at the point x equals 0. Now you might recall from previous math class that a point is a dimensionless location in space. It has no size to it. In other words, it's like a hole in this line that's infinitesimally small. It's so small that nothing can fit through it. It's sort of like when you do painting on your paint programs on the computer. I don't know if you've ever done a flood fill and had a place where you've got an object that had a leak in it, so that when you flood filled the entire page. Well, this point is so small that if you were to graph this function and then try and flood fill below the function, which will become applicable when we get to something called the integral later on. But if you were to flood fill this, you'd find that it wouldn't leak out the top. That point, that discontinuity is so small that the paint on the computer wouldn't come out of it. So anyway, that's why the function or the limit still exists, even though the function goes to infinity. And I know that'll become a problem all year long for you to think about, but I hope that you get comfortable with it as you go. Let me talk about one other thing though as far as infinity is concerned here. And I'm going to erase our initial function. I'm going to take this absolute value sign away from the function. And let's consider y is equal to just 1 over x. Another function that I think you've seen quite frequently through this unit. So I'm going to draw the x-axis and the y-axis, and I'm dotting them because both of them are asymptotes in this case. So now as we draw the function from negative infinity to positive infinity, out at negative infinity it's really close to 0. The limit as this function goes to negative infinity is 0. And then it starts to decrease. And it decreases all the way down to negative infinity. And then comes back into our screen from positive infinity. And then as the x value gets greater toward infinity, the function gets closer to 0. And so the limit out here as x goes to infinity is 0. But let me tell you how I look at infinity, and maybe this will help you a little bit. At least this is what made sense to me. This is where I think they get the symbol for infinity from. I look at this as the function comes in from negative infinity, coming in, and as it bends down toward positive infinity. Now think about something called curved space, and some of you in physics have maybe even talked about that, or you will eventually when you start talking about something called quantum mechanics. This kind of goes with that theory of curved space, that if you go down far enough toward negative infinity, eventually you're going to hit positive infinity and curve back around on itself. So that goes down to negative infinity, becomes positive infinity, comes in the top of our window, and then tends out toward, as it tends down toward zero here, as the x value gets bigger and x goes out to positive infinity, and the same thing would happen here. It goes out to positive infinity, which becomes negative infinity way over there, and then comes back in from the other side of our window. And so we just end up on this continuous loop that just never ends. Now I realize that you would still say there's a discontinuity here at x equals 0. It has to jump someplace to get there. But that was one way that I looked at it that helped me understand why they used this sideways figure 8 to represent infinity, because it, as you graph a function like this, it ends up being this kind of infinite figure 8 loop, and you can't see the rest of it because it's off in space someplace at that point called infinity. But anyway, it seems like most everybody's got a pretty good handle on this. Don't beat yourself up if there's a couple of things that you've felt like you've gotten wrong, but as long as you understand the shapes of the graphs, then we're in good shape. And it looks like most everybody's algebra is pretty solid from what I've seen so far anyway. So I guess as we start this week, what I would aim at is let's try and stay on schedule with the schedule that was printed. It calls for us finishing up, being done with this Unit 1 by the end of September, and October 1st, which is Wednesday, we should be starting the Unit 2 material on derivatives. I'm going to give you a link here, probably Monday, a link for a video that I'd like you to take a look at. It's a video that I've shown to my physics classes every year and showed to my calculus classes when the physics class would get to the unit on velocity and how we find velocity at a point, because that gives us some of the problems that we've been having here with some of the functions, where you end up with finding a function that equals 0 over 0 at some point. How do you figure out what the value is? That's what Isaac Newton actually did in developing calculus, was finding a way to solve for a value of 0 divided by 0. It's not always the same. It all depends on the function that you're dealing with. So anyway, keep up the good work. Everybody's done really well, and I've enjoyed reading your discussions. We've had a good discussion on what do you do to type mathematically, and it is okay to do them by hand and scan them in. Some of you have been doing that fairly successfully. Make sure that you double check that your scans are dark enough. I've had a couple scans where they've been just a little bit hard to read, so you might want to check your scanner or your scanned document before you send it to make sure that it's dark enough to read. But so far it's gone pretty well, and I've enjoyed what I've seen. So let's keep up the good work. Have a good week, and I hope you enjoy derivatives.